Today we learned about standard normal distribution. And standard normal distribution is taking values of something like SAT, ACT, blood pressure, height, things like that, and standardizing them. So you'll hear us talking about renorming test scores to see kind of what the pass rate is. So that's what this is all about. So in a standard normal distribution, you have a bell curve where the mean is 0 and the standard deviation is 1. So if you look at this example, we have 0 here, and then it goes up by standard deviation each time, 1, 2, 3, and then -1, -2, -3. Now each of these pieces, just like you learned the empirical rule, so from -1 to 1, that amount underneath the curve is a certain percentage of the data. And so with our empirical rule, we know that's about 68%. And then if we go from at 2 to -2, that's 95. And then from -3 to 3, that is 99.7% of the data. So this helps us norm things. So we can do some comparisons between people or different scores, or find out kind of, what your cholesterol is supposed to be. They take the norm. And those things change sometimes. Doctors use these, banks use these, a lot of standardized testing, of course, uses these. So colleges, things like that. So a Z-score is a value, a score that helps us find the percentile, or to find where we fit in the population compared to others on a normal distribution. So it's a way to do comparisons to see where you rank. So if you've ever gone to the doctor and they say you're in the 75 percentile of weight or height or whatever it may be, that's saying that you are bigger than 75% of the population. You fall within that percentile. Or you are smaller than 25% of the population, whatever it may be. So a Z-score, if it's positive, it's to the right of the mean of 0, obviously. And if it's negative, it's to the left. So being negative is not always a great thing. We'll look at that in a minute. But these numbers down here refer to Z-score or Z-score. Okay, you'll hear it both ways. So it's very useful with statistics, especially when comparison. So when we're trying to find a Z-score and we have a value of something, let's say we have a raw score of a test, and we want to know kind of where we fit, we use this formula. So Z, finding the Z, equals your value of whatever your test is, minus the mean of that test, so on average, what everybody's average was, and then the standard deviation. And of course, we use other calculations to find the mean, add them all up, divide by the total number, and then standard deviation, of course, and we can do that in Desmos as well. All right, so we're going to do an example to see kind of how this works. So we have a student, Kate. She's at Georgia Tech. She has to take chemistry. That's a gatekeeper course. Everybody has to take chemistry and pass it with a C or better. And she's a freshman. She gets her midterm back, and she opens it and sees a 58. And she probably gasps and feels like she's going to be sick. So she has a lump in her throat. And it's pretty daunting, obviously. But she looks to her left, and she sees a paper with a 37 on it. And she looks to the right and sees a paper with a 41. And she's thinking, well, I did a lot much better than them. So she starts to feel a little bit better that obviously other people did pretty bad. So when the professor tells her that the mean score for this test is a 49, this midterm, and the standard deviation is a 12, she can then take those calculations and find her Z-score. So she takes her score of 58 minus the mean of 49 and divides by 12, and she gets a Z-score, this is her Z-score, her Z-score, of 0.75. So then we use a table, a Z table or a Z table, and we're going to look at that and see what we're talking about. So we're looking for 0.75. So you've gotten a copy of this. This shows you everything that is to the left of the Z-score. So when we think about normal distribution here, and we have a 0 here, and then we got 1, 2, and -1, -2, we know that she fell as 0.75. That was her score. So she's somewhere right around, let's do a different color there. She's somewhere right around here. Okay, so notice that this tells us to the left of the Z-score. So this is going to tell us all the area that falls under here. Okay, so we're going to go look and find 0.75. So on the side of our scale, we have negatives here on this page. It goes all the way to negatives, and then the other side of the page is positive, and we're again looking for 0.75. So we have a 0.7, and so then at the top, you'll notice it says 0.00, 0.01, so we want 0.75. So there's 0.7, so we're going to go over to the 0.5 right here, and this is actually her percentile. So 0.77337 is the area that's underneath that curve in that section. All right, so let's go back to her little problem there. All right, so we have 0.75 for her z-score. However, when we looked at that, we seen that that was the 77, so 0.77. So that means that she scored better than 77% of other people. So when we look at that on a curve, she actually has a C for the midterm. So not as bad as she thought, okay? Because she's within one standard deviation. All right, let's look at a couple other examples. So we have a quick note that, when z-scores are positive, we think, oh, they're great, but that's not always the case. So if we're thinking about like swimming or track or a race finish, obviously the quicker the better. So the lower the time, the better, which will mean that we'll get a negative z-score for those. So you need to think about context, okay? So this is our second example. We're going to compare two different distributions using z-scores to see which is better. So Evan's trying to get into NC State, and he took the SAT and the ACT, and NC State says you can put in whatever one you want. You can give us the SAT or ACT, whatever you want. Well, he wants to send the better one, obviously, to make himself look better. So on his SAT, he scored a 1240. Well, pretty good. But we know that the ACT is scored completely different, and he had a 27 on that. So you can look at that and be like, well, 1240 is better, but not necessarily. You have to look about how that test is scored. So the mean on the SAT is 1081 and the standard deviation of 176. And the mean on the ACT is 18 with a standard deviation of 6. So we look at our SAT and we see that his score was 1240 minus the mean of what the SAT is divided by the standard deviation, and we get a z-score of 0.903. Now, for the ACT, we do the same thing, and we get a z-score of 1.5. So if we think about this in context of our bell curve, if we're putting these on the same one, we have a 0 here, and we have our 1 and 2. So for our SAT, he was about 0.93, so above the mean. So that means he was about right around there for his SAT. However, for his ACT, he was 1.5 above, so here's 1 halfway through, so he was about here. So if we're looking at the comparison, obviously his ACT is much higher overall than his SAT. Now, if we wanted to know how much percentage better, that's when we go to our table and look at the score. So if you look at your table and we say 1.5, we're going to go, we'll take a quick look at that. And we're going to find the 1 on the side. There's the 1, and we're going to go over to the 5. So this would be how much, oh, not that one. Wrong, I'm at 1.05. 1.5, here we go, right here. So he scored better than 93% of the population, because remember this is to the left, so he's right at 93 percentile. So that's pretty good. If we looked at the negative, or the other one, which is 0.903, so here, 0.903, that's not quite right. That's the 0.93. Let's back up. 0.903. He's going to be a little between here and here because this is 0.90. 0.903 would be in between here. So 82 percentile. So obviously if I'm sending it to NC State, 82 doesn't look as good as a 93. So I'm definitely going to send the ACT. Okay. All right. So now let's look at a couple of examples. that you have to know. So when we talk about if something, the chance of picking something out from a SAT score, just randomly pick out the chance of or probability of SAT test score selected at random will fall within plus or minus 1 standard deviation. Remember that 1 standard deviation here and here, that total is 68%. Okay, we memorize 68. This is more detailed as far as the breakdowns. 68%. If we're thinking about 2 standard deviations from here to here, we know that is the 95%. And these relate to your Z scores or your Z scores. Okay. Now, if we have a randomly selected raw score of a 50 and our mean is 40 and our standard deviation is 10, we're looking for the Z score for the situation here, and what is the area under the curve to the right of this score. So let's think about what it's asking. So when we think about, first we got to find the Z score, and we're given the raw score. So we're looking for the Z, and we're given the raw score of 50. We take away the mean, and we divide by the standard deviation. Well, 50 minus 40 is 10. 10 divided by 10 is 1. So then when we look under our table, we can then think about this. Our mean here, this is standard distribution here, but if we put it as our mean here is 40, and every standard deviation goes up by 10, that means that's a 50, 60, 70, 30, 20, and 10, and we fail right here. Okay? So when we use our table, for one, it's going to tell us to the left, all the area to the left. So it's actually going to tell us all of this, what percentile this is. But the problem wants to know to the right of the score. So the problem actually wants to know what this percentage is. Okay, so let's go to our table, and we're looking for just 1. So we're going to go to our table, and we're going to find just a 1. And we see here that just a 1 right here, we have 0.84134. Okay, so when we look, that means that a Z-score correlates to 0.84134 of the area under the curve. So this is our stopping point. All of this over here is 84% of the data. Well, we want to know what is to the right. So for this particular person, they scored 84 in the 84 percentile. So they're better than 84% of the people that took it, even though they just made a 50, which is kind of daunting, right? You think, oh my gosh. So to find this to the right, we just take 1 minus this, and we end up with 0.15866, which is roughly 15.8 or 16%. So this is about 16% of the data. So that means 16% of the people that took it scored better than our person. Okay? All right, let's look at a couple other examples of comparison. So we have a random raw score of 80, a mean of 50, and standard deviation of 10. So if we think about a raw score of 80, that's what we have, 80 minus 50, that's the mean of the test, and divided by 10, that gives us 30 divided by 10, which is 3. That means our Z-score is a 3. Now when you go to your table, we'll go to our table, we'll look for 3. All right, there's our 3 right there, 3.0. So 0.99865. Okay, so 0.99865. So when we think about what this looks like on a bell curve, we look at, this is our mean of 50, standard deviation is 10, so 60, 70, 80, and we actually fell right here. This was our score. So think about how far, we are 3 standard deviations away, so that's pretty good. We did a lot better than the average, okay? So when we think about, when we look at our Z table, it's telling us from here, all of this, what area is under all of this up to our point. Now, it looks like it touches the line, but these never touch the line. They go on forever. We can have standard deviation 4, 5, 6, 7, whatever, Z scores away. Our tables usually don't go up that high, but we can still find them. So when we look at that, we actually scored better than 99.865% of the people. So we did pretty dang good, even though we had a score of 80. Okay? So then let's compare. We have a student 1 that has an 80 score, a mean test of 60, and standard deviation of 10. And then we have a student that has a 40 with a mean of 45 and a standard deviation of 5. So maybe there was 2 different classes. They took the same test maybe. Maybe they took different tests. We don't know. Maybe they're using them as data points just to see if they qualify for something. So we're going to first find their z-score. So if we think about our raw score minus our mean divided by our standard deviation, we have 20, and then divided by 10, which gives us 2. So this is a z-score of 2. Okay. When we look on our table, we can find that the z-score for 2 is 0.97725. Okay. Now, let's go ahead and find this one. We have a raw score of 40 minus our mean of 45 divided by 5. We get a negative 5 divided by 5, which gives us a negative 1. Now, when we look at our table for a negative 1, make sure you're on the negative side. We're looking for just negative 1. We see that that is 0.15866. Okay, so for this one, we get 0.15866. So if we were looking, we could say, okay, this person 1 scored in the 97th percentile. They did pretty good over the class. So they scored better than 97% of the people that took this test in this realm. This person scored only better than 15%, basically, roughly 16%. That's what they scored. So better than 16%. So a lot of people scored better. So obviously, person 1 scored better. But how much better? So if we're trying to look in between these two, we would just subtract these, and then we would get 0.81859, which is roughly 82%. So if we're saying, what's the likelihood of, what percentage would the people in between them fall? It's the 82%. And we'll talk about how to do this on Desmos in a minute, okay? So let's look at this one. We're going to use a calculator to show this one and Desmos to show it. So when we have an area of 0.1700, and it says it lies under the curve of a negative z-score, and it wants us to find the z-score. So if we go to the table, and we're looking for 0.7, and we know that it falls under the negative, we're looking at the negative z-scores, we're looking in here at all these numbers to try to find something that says 0.17. So if I go down and I start looking, now be careful you don't pick 0.017, because there is one on here and that would throw you off. But we're looking for 0.1700. We'll have 0.1787, 0.176, 0.173, 0.171, and then it goes to 16. I don't have anything that says 0.1700, but I know it's got to fall somewhere in between here. Well, this is a negative 0.9, and then this section is a 0.05. So we know that it's going to be a negative 0.95 something for our answer. So we're going to use a calculator to get a more accurate understanding of what it is. Okay, so we're going to flip to just a calculator first. So this calculator version, to use a calculator, you would do second vars and go down to the inverse norm. So option 3 and enter. Now on the new T84s, it'll give you like a menu where you put these things in and then hit paste and enter, and then it'll show up on the older ones. It looks like this, and Desmos looks a little different. We'll talk about that. So we are given the area. So we're doing the inverse because we're basically given the area or the percentage, and that is as a decimal, and we want to put that in and find out what our z-score is. So we're going in reverse. That's why it's inverse. So 0.1700, comma, and then we use our mean, which is 0 because we're standardized, and 1 for our standard deviation. And then hit enter, and we see that our answer is negative 0.9541. That gives us more exact for 1700, or 0.1700. All right, so let's look at Desmos and see what Desmos would do for us. So for Desmos, the easiest way to do this is we're going to put in the normal distribution 0, 1, but we put in front of it a capital N. You can use any capital letter. I use N for normal. and then equals. Make sure it's a capital and equals. And that way you can use that as a code, basically, in the inverse, instead of having to do a whole lot of different pieces. So in the next line, we're going to do inverse period, or the N period, inverse CDF. And you can find these in your function menu with distributions, or just type it in and it'll show up. And then in our parentheses, right here, we are going to put our 0.1700. And notice we get the same thing the calculator gave us. Okay? Now, on the one previously that we did about between the curves, okay, if we are looking about something between something, now we are normally distributing. However, we can take and change this here to what our problem was. And so we were given for that particular problem, different scores. So if we're trying to look at between two things, those things can work if they're different between two different things, the norm. So we can put between the scores here. Like, let's say we're doing something in the standard and we're going, the top range is 0.97725, and our bottom is 0.15866. We can see that would give us the range as far as between what our area is. Well, we want to know between the Z scores, right? So we would do our max here as 2, because we're normally distributed, and this was our previous one, 2, and our bottom one as -1. All right, so then we see kind of what is in between. Oh, I did 0.2, not 2. It's like, that's not right. Now, we would see that that is all the area in between those, and it highlights it for us between. So we can't put in what we get on the area for that. We have to put in our Z-scores if we want to know in between. There are other ways to do it if we are dealing with the same mean and standard deviation if they're two, but this is the one previous where they had different means of standard deviation, and we normed them and found their Z-scores. So we can find the difference between the two. All right, let's look at a couple other examples. So we have lifeguards are going to be hired, and they want to see if they can make the cutoff for the top 20%. So we want to deal with the top 20% of our people. Now, notice that they have a mean score of 120 and a standard deviation of 10, and they want to know what the cutoff is. So if we think about our standard curve here, we've got 0, 1, 2, -1, -2. We could do our -3 and 3. All right, so if we think about what's happening here for this particular one, we have some values. So we know that the mean is 120, and it goes by standard deviation of 10, so it's like 130, 140, 150, and so on. And then 110, 100, and 90. So we would want to find where the top 20% is of the applicants, okay? So we're looking for this upper range here. We're not looking for the bottom 80%. So we're going to think about the bottom 80% as being our Z-score. So we want to know the bottom 80% of this area covered, whatever it may be. So like we know that this is 50%. So we know it's going to be some more over here, okay? So we got to find out what it is based on this. So you can use your formula that we had Z equals the raw score minus the mean divided by the standard deviation. We don't know the raw, but we can say we want everything to the left is 80%. We want the top 20. So 0.80 or 0.8 is equal to something we don't know, that's the cut score we're trying to find, minus the mean of 120 divided by 10, and when we work that, we get 8 equals x minus 120, and solve for that, we get x equals 128. That means that the applicants on their fitness test need to score 128. So here is 120, about 128. All right, so this over here is the top 20% of our data. And that is what we're looking for, so 128. And there's a couple other ways to find that. In Desmos, we could do some situations with that as well, and we worked on some of those in class. All right, number 6, we've got scores at the SAT test are normally distributed with a mean of 500 and a standard deviation of 100, and your professor scored 500 in math and 450 in verbal. So we want to know what his Z-scores are. So 500, we're talking about math here, we got 500 for his score, and for verbal we have 450. So we want to use the standard deviation and the mean. So the mean for SAT 500, standard deviation 100, and then 500, standard deviation 100. So for this one, 500 minus 500 is 0, so this Z-score is 0. And for this one, we get a negative 50 divided by 100. And then when we reduce that down, we're going to get a negative 0.5 for that Z-score for the verbal. Okay, so obviously if we look at this and we think about our bell curve, if he was here for math and he was at a negative 0.5 here, he was verbal, he obviously did better in math than he did in the verbal. Now, how much better? Well, if he's at math here, he scored better than 50%, because half of this is 50% of the population, but 50% also scored better than him. So we get to our next question, what percentage of people who took the SAT scored better than your professor? Well, 50%, because he was right at the middle, so 50%. And conversely, how many people did your professor score better than? Well, he scored better than 50%. Now, when we look at the verbal, we want to know the percentage of people who took the SAT that scored better than your professor. So we're going to have to do a little bit of work. So our Z-score for our verbal was a negative 0.5. So let's look at our table, and let's go to our negative 0.5, and we'll see that here is our negative 0.5, and this is for the 0, 0. So he had a 0.30854. So let's look and see what that looks like. All right, so if we have a table or a little curve here, and we have a 0 and a 1 and a negative 1, and we know he is right here at negative 0.5. This is his verbal. And our table tells us to the left. So this, all this right here is what our table told us. And it told us that it was 0.30854. And this question says, what percentage of people who took the SAT scored better than your professor? So for that, we're looking on this other side, this right side. So we would have to say 1 minus 0.30854. And that would give us 0.69146, which is approximately 69%. Okay? So we know that 69% of people scored better than he did. And what percentage of people did your professor score better than? Well, that was pretty easy. We already had that in the left, so approximately 31% he scored better than. So I'm not sure if I want that professor teaching me anything to do with English or things like that. But we do know the standardized tests are just one data point, and that doesn't define who you are as a learner or a person or a teacher. So they just might be really bad at taking tests. Might have had a bad day. All right, hopefully this helps. I'll add some more resources for your convenience on campus, and I'll see you soon.